I'm taking it over.
All right. Welcome everyone so far to the stream. We can start a couple of minutes early. That's not a problem at all. Okay. Now, obviously, this is our first stream for the level 3 it's the differentiation topic today. I've done a few streams this last week already for level 2 and level 1, which was a lot of fun. Yeah, today, of course, we've got you guys differentiation. There will be 2 streams for differentiation. There will be 2 streams for integration and 2 for complex numbers. All of them Mondays from 6:30 to 8:30. And of course, they will be uploaded afterwards, so you guys can refer back to them, do some more practice questions later, or if you missed it or you couldn't make it, you can share those with your friends or anyone else. Now, for the stream, of course, the chat should be available with low latency. That means you guys can ask questions as we go. Yeah, and you guys can let me know what you guys want to do. Yeah, as long as we don't have that many views, we can kind of change the topics as needed. Yeah, depending on how many people will join later, I have a few topics that I've got already planned for today, but we're pretty flexible in terms of what we do. Okay, let's have a look. Okay, so the first part that I've got here, what is it, black behind me? I don't know. Okay, so for today's topic, yeah, as we said, but also I have a full course on the complex number topic, and I know that most of you guys will be doing the complex number exam at the end of the year as well. So I think there's like 9 videos of like 10-15 minutes each with all the concepts that you need to know. Yeah, and wonderful. Okay, so these are the kind of the topics that I had a look at for today. We're going to basically make sure that after today we know all the fundamentals. We have practice and revision for how to differentiate all kinds of functions. Because of course we can't solve any questions or answer any text questions if we don't know exactly how to differentiate all of the different questions, right? All of the different functions, power rule, chain rule, quotient rule. I mean, you guys have all covered them in school already. Yeah. Remember in the chat, yeah, if it's too easy or too difficult, yeah, let me know, because as long as we don't have that many people, we can be very flexible. Now, after today, we should all be able to get the achieved and some of the merit questions done in an exam. Yeah, it's very important that you guys know how to do all of these. Most of these will come in the exam. I think there has only been 1 exam in the last 4 years where each and every single one of those topics wasn't covered. Okay. Absolutely, yeah, we've basically already done that. So let's have a look at the very basic one, which you guys know from year 12 as well, the power rule. Yeah, I've kind of copy and pasted some parts of the formula sheet in, and we've got some examples where we can just see how to do these again. So remember, anything that has an x with a power, the way that we differentiate that is by multiplying the power to the front and then reducing the power by 1. So this is basically what this rule is telling us. Let's just do a few examples. I mean, this one I'm pretty sure you guys are pretty happy with. So let's have a look at our first one here. We have f of x. Let me do it in blue. I like blue. F of x is x to the power of 5. So of course we have the 5 moving to the front, which is going to be 5x to the power of 4, reducing the exponent here by 1. Yeah, so we're going to get f prime of x is equal to 5x to the power of 4. Now, for the next question, we have 7x to the 3. The 3 is multiplied to the front, which is going to be 21x. And now the power is reduced by 1. So from 3, it's going to get to 2. If you have a question like for number 3, where there's a fraction, what I recommend is rewriting this. Yeah, so here if we have, I'll actually make this a little bit bigger so we have more space to write it in. This question here I would rewrite as 1/4 times x to the power of 6, and then you guys can just simply apply the rule that we know. So we have f prime of x is equal to 6 times 1/4 x to the 5. And you guys have a calculator, so just chuck it in the calculator if you need to. For number 4 and number 5, it doesn't actually matter if we have negative powers, if we have fraction powers, if we have decimal in the powers, the same rule applies. So we're going to do exactly the same thing. So over here with number 4, they're a little bit crowded. Apologies for that. Here we have f prime of x. For number 4, -2 goes to the front, x, and then we reduce the power by 1. Yeah, so remember reducing is -1, -2, -1 is -3. That's this example here for number 4. Okay, now the only one here that I kind of want to do is number 6 and number 9. If you guys want to pause the video and make sure that you're comfortable doing all of these. Let's have a look at number 6 here. Yeah, so we have 5/x cubed. Yeah, so we have f of x is equal to 5 divided by x cubed. And again, we have an x with a certain power. Yeah, so here, if we have a fraction, we don't really want to have a fraction. From level 12 or from level 2 in the algebra section, you guys should know what it means to be in the denominator with a power. That means we can take it out of the denominator by having a negative power. So this is just an algebra reformation, changing it up. And now we can take our derivative with f prime of x is equal to, and now we apply our rule. The number in front multiplied by 5. So we have -15. And we have an x, and now the power is reduced by 1, so it's going to go to -4. And you guys don't have to change it back. You guys don't have to simplify. I would just do the numbers in the calculator. That's all you guys, that's all I would do. But no simplification once you have found your derivative is required in any way for NCEA for the marking schedule. Yeah. I will also do number 9 here, but if you guys have any specific examples here, you can put it in the chat now that you want me to go through and do. Otherwise, I'll start with number 9, which is the cubic root of x to the 5. It was the cubic root of x to the power of 5. So for this question, again, we have a square root here. Yeah, you guys should know that square roots or cube roots or all of those radicals, yeah, from the complex number part is a fractional power. And you actually have a rule or you have a formula. I think it's in the formula sheet as well, where you have the x to the power of n over m is equal to the mth root of x to the n. If this is not on the formula sheet, I might check that in a minute for you guys. Then you guys need to just remember one thing, and this is what I teach all my students as well. Just remember that the square root of x is equal to x to the power of 1/2. This is the only one you guys need to know, because then we can match these n and m's ourselves. We know that this is a square root, so that means that is where the 2 comes from. Technically, it's a 2 root. And as long as we have that one, we know that the other number will have to be this part here. And that is exactly the same match as we have in the formula sheet above. So this is how I remember this formula. So if we now apply this formula over here, we know this is a 3rd root, and we have 5 to the power here. So we can transform this simply by having a 5/3. And once we have changed this algebraically, we again have our power rule, so we can apply our general rule here for our derivative g prime of x, which is just having the exponent multiplied to the front, and the lucky thing is there is nothing in front, so it's just a 1. That becomes 5 over 3, and then we have x to the power, and now remember we need to take 1 away from the exponent, and you guys are more than welcome to just write this and put this in the calculator. Yeah, this here is the power. You guys can just chuck it in the calculator if you're not sure how to do fractions, you forgot how to do fractions and minusing, plus doesn't matter, you guys have a calculator. This is again the only thing that I would encourage you guys to put in the calculator, which is just the numbers. I wouldn't simplify anything else. So in this case, just for clarity, 1 is 3 over 3, 5 over 3 minus 3 over 3 is 2 over 3. And this will be the answer. Now, I think you guys should be pretty good with these ones. Yeah, these ones are returning questions from year 12 as well. So let's have a look at one of the first rules that we have here that was introduced in year 13. And this is the product rule. And I've just copy and pasted the top part, yeah, from your formula sheet. Yeah, this is exactly what it says in your formula sheet. You guys can use either one of those, but I highly recommend just using the first one. And the way that you guys can use this one is, well, we can see here f, g are the functions that are in that order, f and g, and that's what we're differentiating. And we need to put them in this order. So let's have a look at our first question here. Our first question over here is f of x is equal to x squared e to the x. The hard part in the exam is always figuring out if it's product rule, quotient rule, chain rule, or whichever one you need to use. So I highly recommend remembering, yeah, the very standard ones, like x to some power is one. If we have a root of x is one. Sine of x is one part. All of these are simple, like one part, easy equations or formulas. Of course, we have cosine, we have tan, we have e to the x, we have natural log of x. All of these are one part. So if you see them next to each other in any order or any combination, that immediately means product rule. Yeah. How do you guys know what when this one is? This is when things are times together. Yeah. Product is the result of a multiplication question. So 3 times 4, the product is 12. Yeah, that's why we need to use it whenever we see multiplication. So we're just going to go straight forward and have a look at our first one. This is going to be our f, and then the second one is going to be our g. Exactly like we have it in the formula sheet, if you guys want to check that one out. Yeah. And then we're going to write down f prime of x, the derivative here, and we're just going to follow the formula. The formula says f times g dash plus gf dash. So what does that mean? We need to have each of these parts. Yeah. And I don't know if you guys want to do this. Let me know if it's too fast. Yeah. I'm just going to differentiate them as we go. Or but if you want me to write them out, what f and f prime, g and g prime are, yeah, let me know if it's too fast. Yeah, every student is at a different level, so chuck it in the comments. Okay, now in order to find our derivative here, we're going to have f first. F is the green part, so we're just going to copy that. That is x squared. And then we're going to multiply by g prime. Now g is e to the x. The derivative of e to the x is e to the x by itself. Again, yeah, it's its own derivative. And the next part is plus g. Now g is again copied, so we're just going to have e to the x. And then we have f prime. Well, f prime is the derivative of x squared, and that's the power rule that we just did. 2 moves to the front, reduce the power by 1, which is 2x. If you guys want to, you can put a multiplication in between them, or you guys can put them in brackets. I like putting a lot of things in brackets instead of writing multiplication, but it's up to you guys, whatever works for you guys. Do not simplify here. Don't factor out the e to the x. If you make a mistake simplifying, sometimes they count that as you're working. So just leave it as that. Nothing is required for the differentiation topic in terms of algebra. Right, let's have a look at the second question. We have 3x cubed times the natural log. Yeah, so that's the second one. So here we have f of x is equal to 3x squared times the natural log of x. Now, for this question here, again, we see two parts. Yeah, this is one part, which is a polynomial, and ln x is the second part. Let's again write this one as f and the second one as g. And again, we're following our formula. We're going to have fg prime plus gf prime. So f goes first. So the derivative here is equal to copying f, 3x squared, multiplying by the derivative of g. Yeah. I think I've got a formula sheet later on with all the different functions. Yeah, but the derivative on natural log is 1 over x. Now we have to copy g, which is the natural log of x, and the derivative of f. Well, that's again the power rule. 2 times 3 is 6, and x reduced the power to 1 less. And again, you can put a multiplication in between. You can simplify this, of course, but for any achieved merit question, you can just leave it exactly like that for your mark. It will, I think, usually tell you as well that simplification is not required. Now, we have a lot of examples. So if you guys see any examples that you guys want me to cover, because I'm just going randomly through some of these examples, let me know in the comments, and that's the first one I'm going to do after that. Yeah. Which one do I feel like doing? I think we could do number 6, because number 6 has a couple of options that you can have. So we have x to the power of 3 plus 1. And we have x squared minus 4. Now, if this is our question, what we could do is we could expand this. We could expand it all the way, get a polynomial. We have multiple parts with x to some power, and we can just apply the power rule, which is perfectly fine. If that's how you guys want to do this question, no problem. Expand it. And then you're done. So let's just expand real quick. We're going to get x to the power of 5, which is this one, and then this. So then we're going to get minus 4x to the power of 3 plus x squared minus 4. Just expanded that real quick. Yeah, expanding is definitely what I would do. It's very easy here. But of course, that is not what we're trying to learn here, right? But the thing is, always be smart. Always look at what you can do, because there's always many different ways to solving a question. My way is not always the best. Maybe you have an idea on how to solve something better. And as long as you get to the answer, that is always the best way. Yeah. So now we have f prime of x here. 5x to the power of 4. 3 times negative 4 is negative 12. So we get negative 12x to the power of 2. Plus 2x, and we didn't really talk about this, but constants, so numbers just by itself, they are 0. Hey, welcome everyone in the chat. Hope you guys are doing well. We're just working on the differentiation topic, the fundamentals. Okay, now if we wanted to apply the product rule here, we definitely can, because we have two things that are multiplied together. So let's quickly do that. We have x to the power of 3 plus 1 times x squared minus 4. Can I move it over? Yes, I can. There we go. Now, how does the product rule work? Yeah. we have fg prime plus gf prime. That's in your formula sheet. So let's have a look. We have f here and we have g. And let's just copy. First thing, we copy f, x to the power of 3 plus 1, and then g prime. Now the derivative of this, well, that's 2x by itself plus 0. And then we're going to have g, which is x squared minus 4, copied, and f prime, which is 3x squared. And I mean, you can argue that this is easier because it's a one-step answer, but the good part is you just don't have to simplify. Yeah. So for anyone who has to simplify or do some actual work with these questions, this would be the best approach. But since you guys don't need to do any simplifications, I mean, go ahead. Either way. Okay. Yeah, are there any preferred questions that you guys want to see over here? Or maybe you guys can put in the chat how you guys are doing at the moment in math. Are you guys hoping to pass this year, or are you guys hoping for merits or excellences? Is everyone happy with the product rule here? Okay, we can move on to the next one. If someone else wants to see one of those questions, we can come back. Okay, now the second part here that I have copied from the formula sheet is the quotient rule. Now, quotient is the result of a divided by question, right? So that naturally means we need to have a division, yeah? And most of the time we have a fraction. If you guys see a fraction, this is your go-to method to do the derivative. And this is what's in the formula sheet. And again, this part here, I mean, that is perfectly correct. And it's a way of writing this in with the Laplacian, not Laplacian, what is the, I forgot the mathematician's name who did this this way of writing the derivatives. Oh, how did I forget that? Yeah, but what I was saying is this part here, you guys don't really have to worry about too much. It's very messy. I like the easy F and G. Hi, Movies. How are you doing today? Feynman? Is it Feynman? Oh, I'm sorry. I have to look it up now. It's not Newton, right? Damn, who can find it the fastest? I don't think it's Feynman. Is it Newton? Is it Newton? Oh, let me have a look. Leibniz, that's the one. Oh, how could I forget? Yeah, the Leibniz notation. Ah, oh, okay. How could I forget? He's a German mathematician as well. Very, very sad here. Okay, let's have a look. Now, again, we have an F and we have a G. And as soon as we see any kind of fraction, we're just going to have exactly that, F and G next to it. And then we can just blindly copy, no simplification needed. Yeah. So if we wanted to find the derivative here, f prime of x, we're going to just copy what the formula sheet says. We start with a g. So the g here is the bottom. Yeah. So this is x plus 1. And just be careful every time we talk about this as a g or this as an f, just like substitution, we're using this whole thing. It's kind of like it's got a box around it. So whenever you replace it or use it, you should put brackets around it because that's the whole part of g. So we copied g. Now we need f prime, which is the top differentiated, which is 2x. And that's why I like doing brackets instead of multiplication. It's easy to keep track. And then we're going to have a minus copying f. Copying is easy. And the derivative of the bottom, which is just 1 and 0. So 1. And then it says g squared at the bottom. So we're just going to do x plus 1 all squared. And again, no simplifications. Don't do any of that. Yeah, if you guys are asked to find the gradient when x is 1, just substitute in 1 and put this whole thing in the calculator. Yeah, so if it says what is m when x is, let's do 0 so I can calculate it easier. Then all you got to do is find f prime of 1 and substitute it in, put it in the calculator, and don't worry about anything else. It's just going to be 0 plus 1 times 2 times 0 minus 0 squared over 0 plus 1 all squared. This part is 0. This is 1. 0 plus 1 is 0. 0 minus 0 is 0 over 1. So the answer is 0. A very good example. I don't need a calculator. But if you needed to, just copy this whole thing in the calculator if you wanted to find the gradient. Right? Okay. One more question. I think this one's too easy. Let's do something with trigonometry. We haven't really done that much yet. Yeah. Now here we have again a fraction. Every time we have a fraction, we just apply the quotient rule. So we have f over g, and then we have the derivative of f of x here is equal to, now if we want to have a look, what was the formula? Yeah, we have gf dash. Yeah, so we have gf dash minus fg dash over g squared. And we're just going to copy g. That's an easy one, copying g. Now the derivative of sine is cosine. So we're going to multiply by cosine x minus f, which is the top, which is copying. That's an easy one. Multiplied by the derivative of the denominator, that which is 1. And we're squaring the bottom. We're just copying the bottom, whatever it is, putting a squared around it, and that's done. I think the quotient rule is one of the easiest questions they can give you, because they can literally just, it's very easy to identify when to use it, and it's very easy to just apply. You just copy whatever the formula sheet gives you guys for an achieve mark. There's some more questions over here. Yeah. Is there any of these that you guys want me to do? So they're a little bit cramped. I just basically got lots of examples so we can have a big variety of questions that we can go through. I think they're all pretty easy as long as you follow the rule. Maybe we'll do number 7 because the 7. Let's do f of x is equal to the square root of x over x plus 4. So how do we find the derivative here? Again, we have a fraction. So we have f over g, and our formula is gf prime minus fg prime. Okay, and now we're just going to go and copy g. So we have the derivative of x here is equal to g, which is x plus 4, times the derivative of the numerator. And again, the numerator has a fractional power. Yeah, remember the square root of x is x to the power of half. So if we differentiate that, that gives us half x to the negative half. Yeah, multiplying the half in front, reducing the power by 1. And then minus, we're copying f. And now we can go back and using the square root because we're just copying. And g prime is the derivative of the bottom. This is 1 and this is 0. So the derivative is just 1. And we copy the bottom very blindly without doing anything, squared, and done. Again, you guys can pause. You can give these questions a try. Okay. The next part that we have is composite functions. So we have the chain rule. So how do we do this? These ones, again, don't worry too much about this at the moment. This is actually quite good in in comparison to the other ones if you're going to be doing some of the other questions, like, for example, parametric equations. Yeah. For those ones, this notation is actually very good for the chain rule. We might do some later. We'll see how far we get and how everyone is going today. So with these ones, it's mainly the recognizing part where my students struggle. So when I get students, the hardest part is to figure out when we have an inside function, when we have a composite function. So basically what I usually say, if you see brackets, yeah, so rule, if you see brackets, 90% of the time, that's chain rule. Yeah, not necessarily if you are multiplying them like we did in the beginning, but most of the time, anything in brackets is usually chain rule, because when you have something in the brackets, like here, 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 and all of those questions, all of those are functions itself. Another way that I teach my students to recognize when there is a chain rule is to make sure that you guys think about the standard versions of a function. So for example, here we have sine of x. This is the standard version of the function that you guys know. If it's not an x there, if there's anything else, it will have to be chain rule. Yeah. If you have the square root of x, there's something underneath the square root, like in this question over here. Again, this is chain rule, because basically this is in brackets and all of this has the square root applied to it. Now, for these, I think the only thing that you guys need to remember is to always differentiate the outside first, then multiply by the derivative of the inside. So let's have a look at our first question here. We have f of x is equal to x squared plus 1 all to the power of 5. Now we could expand this, but this is going to be a very long way of doing the work, because that's going to be half a page of work. But on the other hand, what we can do is we can see that this whole thing here is in brackets. So if we now assume this whole thing, the yellow thing, is just by itself to the power of 5, then how would we do that? Something to the power of 5. Well, the 5 would multiply to the front and then reduce by 1. So we're going to get 5 multiplied by, and we just copy everything that we have in the brackets. Hi, how are you doing? Nerd Vlogs, love the name. Okay, we're reducing the power by 1, so we have 4. And recognizing that this is chain rule is the hardest thing for a majority of the students. They always forget to do these. Now we have differentiated the outside. The last part that we need to do now is multiplying by the derivative of the inside function. So we need to take whatever we copied here, take the derivative, which is 2x, and multiply it by the end. Right. Let's have a look at the, let's do this second example here, sine of x cubed. F of x is the sine of x cubed. Now, again, the hardest part is to recognize it is chain rule. We see something in brackets and it's a function, so it's chain rule. If we want to differentiate this part here, we're going to differentiate sine. Sine goes to cosine. You can look that up in your formula sheet. So we have cosine, and it's always copying whatever is the inside function. Always just copying it. And then we have to remember to multiply by the derivative of whatever we copied. So in this case, 3x squared. Again, don't simplify anything. Leave everything just like that. If you guys need to use it to find the gradient by substituting in a value for x, literally just do that. If you have x is 0, you can find the f prime evaluated at 0 by doing cosine of 0 to the power of 3 times 3, 0 squared. And of course, this is 0 multiplied by this, which is 1, is also 0. Oh, did I make a mistake? Cosine x times 3. Let me have a look. So sine goes to cosine, yep, and then we multiply by this part, which is the derivative of this part. That should be correct. Yeah. So it's always the inside part, yeah, that we use for the derivative, and we can ignore everything else once we've copied it, right? Is there a specific number that you guys want to do? I am from New Zealand at the moment. I'm streaming for the New Zealand end of year exams, but my original inheritance comes from Germany. Let's have a look. Maybe we can do number 8. I think number 8 is, or number 9 is good. It's the number 9. So we have f of x is equal to e to the sine x. Now, again, how do you recognize how to do this question? Well, it is a chain rule because we can see where we usually have an x, like e to the x, we actually have a function. Nice. What is the exam in India? G exam? No, I don't know Kanye Williamson. Is that should I Google that one? Is that a mathematician or something? Oh, it's a is it a footballer or something? Someone in sport, a cricketer. No, I don't watch too many sports shows. Sorry. Oh, he does engineering. Okay. Is it not cricketer? Did you guys just make me Google something weird? Chat, what are you doing? What are you doing? All right, let's finish this question over here. So we have f of x is e to the sine x. We know it's chain rule because we have a function here at the top. Now, how do we take the derivative here? The derivative of e to something is just copying it exactly the same way. That's how you do the derivative of an exponential, but we multiply by the derivative of the inside function. So the derivative of sine is in this side cosine x. And again, here we have the inside function and its derivative multiplied at the end. Nice. I'll have to keep in mind who this Kanye Williamson is. Do you guys have a specific question you guys want me to do for this one? Or are you guys happy with chain rule? All right, I think we'll move on to the next part. If you guys want to let me know in the chat, I can always go back. Okay, so for differentiating of exponential functions, we've kind of already done this. The rule for exponential function is to make sure that we're just copying it exactly how it is and multiplying by the derivative of the top. So for the first one, if we have e to the x, that is e to the x differentiated, multiplied by 1, right? But we don't need to write it. If we have 3e to the x, again, the number in front stays the same, 3, and we differentiate e to the x times by 1. Let's do a little bit of a harder one. Let's do number 5, 5e to the negative x. So if we differentiate this part, again, the numbers in front stay the same. E to the negative x stays the same. We just copy it, multiplied by the derivative of the inside. So the numerator, not the numerator, the exponent here, which is -1. Yeah, it's very easy to forget to multiply here by the chain rule. You're doing software engineering, Abbas. Is it safe, in your opinion, in future? Scope of this field in New Zealand? I think there's a lot of job opportunities for engineering, but I'm not really sure on what the job opportunities are like here. I know that there's a lot of people studying engineering, so it must be good. Appreciate your feedback. Yeah, basically just helping everyone else as much as I can. Why is the derivative of e to the x e to the x? Well, the rule that you guys just need to remember is that e to the x, if you differentiate it, it's the same thing. If you differentiate e to the x, then you just get e to the x multiplied by the derivative of the inside function, which is 1. But why that's the case, there's some proofs that you can follow on why e to the x is its own derivative. I think it's the only equation that it's its derivative in a general form. Abbas, can you tell me the clean difference between differentiation and integration? Absolutely. So there's two parts, right? If you're doing differentiating in terms of applying the rules, yeah. So you have all these rules that you apply to the functions to differentiate. They're obviously different rules than integration. You need to do the opposite in order to get the integration done. Yeah, there's a lot of different other rules, but from concept knowledge, differentiation and integration are very much related. They are opposites of each other, just like plus and minus, or times or divide by. And if you differentiate one of the functions, you can integrate to get back to the original, just with a slight little difference because you have that plus c at the end, right? And differentiation is mainly used for a few things. If you differentiate a function, that gives you the gradient function. Let me put that here. So if we have f of x here, and we differentiate and we get f of x here, this is your gradient function. This function gives us the gradient at every single x value for the original function. Here, this is the original function, right? And the integrated function, yeah, if you integrate, let's say we integrate f of x here, make a capital F of x. If this is the integral, there's also certain applications for this. Yeah. So if you want to find the gradient, that's one part. Yeah. Finding the gradient is often used in optimization, which is finding maximums and minimums of equations or functions. This is usually where this is used very, very much. For example, if you manufacture a can of tomatoes, right? What is better? Do you rather have like one of those long and short ones that you usually see for like tuna, or do you want like a really high one to store your tomatoes? Because you could use any. And if you wanted to optimize this in terms of the amount of steel or material that you use to build this can, you can find the perfect solution to have the lowest amount of surface area compared to the others, right? And therefore lowest cost to manufacture. So that's one part where differentiation and optimization comes in. And the other part, of course, is that we can find gradients at all points where it's difficult to see. Yeah. For example, we can write the tangent equation or the normal equation. Yeah, the tangent equation is a line that touches the equation just, or the function just at that exact point. And if you zoom in a lot, then it actually has the same gradient there. Yeah, integration is definitely much harder than differentiation. And if you kind of need to be pretty good with differentiation in order to get good at integration, right? Some rules, like the power rule, is something that you can easily do, right? Instead of doing x to the power of 3, if you differentiate that becomes 3x squared. Move the power to the front, then minus the power by 1. And then, of course, if you integrate it, right, I should do this so you guys see it's differentiated. But if you integrate x to the power of 3 with respect to x, let's not be too lazy here, then, of course, the rule is basically the same, just in different steps. First, we increase our power by 1, then we divide by the new power, right? And we have to add the c at the end. So differentiation is much easier than integration. And the thing that makes it so difficult for integration is that there's a lot of questions or a lot of functions that can't actually be integrated or very difficultly. Yeah, there's methods that we use with a computer to get a numeric solution, and that is very often used in mathematics because we simply can't find integrals of very difficult equations, right? Just to finish off our little diagram here, what is integration used for? Often there's 2 or 3 really cool things that are, that happen with integration. And the one part is to find an area under a curve, right? So if we have our equation over here, integration will find the area under a curve if you have a this part here. If this is f of x, here's the x-axis, and here's f of x, and this is our function f. Then this part here, from a to b, is the area is equal to the integral from a to b of our function f of x dx. And I think this is a really cool thing, that you can find the area of lots of different shapes. And another interesting part about integration is when you want to find a volume, for example, of some shape that is really odd, right? Let's say you have some vase or something like, I don't know, I can't really draw very well, but let's say we have this this thing where you put like your flowers in, right? And you wanted to find the volume of this. Obviously, it's a weird shape, and the best thing would be to put water in it, measure the water, and then find the volume. But of course, that might not be what we want to do when we're producing it, not as accurate. So what we can actually do is we can have a function, let's say something like this part, and instead of integrating it, yeah, if we have the integral from 0 to 1 of this function f of x, that would give us the area, but we don't want an area. We want a solid. We want like a vase-looking shape. What we can do is we can rotate this around the y-axis, and then we kind of get this this vase-looking shape. And of course, this is in 3D, yeah. And this is no longer the integral, but it's a little bit different. But what we can do is we can rotate this shape around the y-axis to get a 3D solid. And we can find the volume here using integration. Differentiating is breaking fn into small pieces. Integration is joining of small pieces. Yes. So if you do differentiation, right, a lot of the times you want to find the gradients. So if we have a function here, f of x or f, if we want to know at this point over here what the gradient is, what we do is we kind of zoom in as much as we can. And then instead of having our line, we're going to have a straight line kind of replacing our equation, right? We're replacing it over here. Yeah. And it's still not going to be perfect everywhere. So we can technically zoom in more. I can't zoom in anymore on this canvas, but the more and more we zoom in, the more we can see that this one line here is actually looking exactly the same as our equation at that one singular point. And here, of course, we can find the gradient of that straight line because we know this is rise over run. Yeah, for a straight line. So once we know this, we can say, well, at this one exact point here, x0, x0, we can figure out what this gradient is. But of course, that only tells us how steep it is, and it's different for each point. So if we wanted to know it for here, of course, if we wanted to now draw this tangent line over here, it's different from the green line. So the gradient here is different. Yeah, so it basically becomes a straight line at a very, very tiny interval, like at the exact point, actually. Yeah. This is actually where all of the differentiation part is coming from the definition. Now, for the New Zealand curriculum, it's really funny. They have it in there, but they don't actually, they don't really mark anyone on it. Yeah. Knowing what differentiation and everything is and where it comes from is not really required. But differentiation comes from a concept called limits. Are you guys familiar with limits? So, yeah, a little bit. Okay, so basically, limits means we want to get something as close to each other as we can, right? So we want to limit something into infinity or something, the concept of keep going. And that's exactly that zooming in part. Yeah, if we have our curve and we want to make it a straight line and we zoom in and we keep zooming in and so on. The more we zoom in, what we actually are going to see is that our curve here is going to have 2 points. And they might be very close to each other, yeah, but they're not going to be exactly the same. I'll draw them a little bit further away here, yeah, to make it kind of clear. This part here, yeah, is the connection between those 2 points. And we can see that that's not really the same as our curve. So what we're going to do is we're going to take our point here, let's call him P1, and instead of having him here, we're going to have him over here. Now, this line here looks a little bit better at estimating what this curve looks like, but it's still not good enough. So we're going to move him further, and we're going to move him further and further closer to our second point, P2. They're getting closer and closer, not actually getting there. And the more closer we get, and I'll just draw a single line here, the more we can see that this straight line that we're creating with 2 points is actually looking like our equation. And now when we look at limits, yeah, we want to be infinitely close. And you can imagine the closer I get with our point P1 to P2, the closer we get, the more that red line that I'm drawing, let me get rid of this, the more it's going to look exactly like that curve. And if we get like to a millionth number, very, very close to each other, and even closer and further, then we can kind of see that at that point where we're approaching it, our straight line, the gradient of the line is equal to the gradient of the curve. And sorry about that. There we go. And that's kind of where we come from, right? You can have a look because this is mainly for the NCEA students. I'm not going to go into the full proof or the full idea on how the derivative is created. But basically, this is the idea that people have had, that we're taking these points and we're moving them closer and closer. And if we then have the gradient of these points, and we have rise over run is the gradient for a straight line. If we're looking at this is the difference in the y values of the x points divided by the difference in the x values. And if we're now using this, you can have a look. I think it's on Wikipedia or something. You can have a look on how this proof works. There's a nice little picture with it. Too much for me to draw it. Yeah. Okay. So let's get back on track on where we were. So if we are doing all of these questions and differentiating these questions correctly, then the next part for us would be to answer some questions on using differentiation. So here, is this the last one? We just have a couple more examples. I guess we might as well quickly do them before we do some of the achieved style questions. Anytime we have a natural log, of course, the way that we differentiate this is 1 divided by. So let's have a look here. The derivative let's start with number 2, because number 1 is kind of just like given to us in the formula sheet. The derivative of natural log of x is 1 over x. That's kind of in our formula sheet already. So if we are looking at number 2, the natural log, if f of x is the natural log of x squared plus 1. The way that I always do natural log questions when I do the derivative is very easy. So we're going to do the derivative. It's always let me put the rule over here. So the rule, the numerator is the derivative. Sorry, it's not very easy to see. The numerator is the derivative and the denominator is copied. There you go. So if we wanted to differentiate something with natural log, well, whatever is in the brackets here is going to be on the bottom, x squared plus 1. And if we take the derivative and place it on the top, we get 2x, and that is our question done. That's our derivative. Why does this work? Well, because technically the derivative here is 1 over x squared plus 1 multiplied by the derivative of the inside function. But the way that this always works is that we just move the single part to the top of the fraction. And the reason why I make all my students remember this rule is because it makes it easier later on when we need to integrate. Because when we integrate, there's actually a formula on the formula sheet which says that f prime over f, if we integrate f prime over f dx, then we get f back, natural log of f plus c. So this is a formula that's on the formula sheet, and it's a concept that we need to know for integration. And just like we said earlier on, integration is much harder. So the easier we set ourselves up for integration, the much more success we're going to get. So every time we have natural log, we just copy the bottom and differentiate it, and that's the numerator. Let's do an example. Let's do number 4, natural log of the square root of x. G of x is the natural log of g of x. Oh my god, what am I saying? Of square root of x. Yeah, you're correct. Did I get it correct? Yes, I did. Yeah, absolutely. So again, how do we do? Very easy. The derivative here is just copying the bottom. So square root x, and we're not even going to make it to the power of half or anything fancy. We're just going to leave it like that, copy it, and then the numerator is the derivative of the top. Well, the derivative of this, we've had this before. Yeah, remember we had the square root of x is this x to the power of half. So if we differentiate that, we need to first switch it to a power and then use the power rule. Half moves in the front, then reduce the power by 1 makes negative a half. And I wouldn't even use any algebra here. I mean, we could, but for the marking schedule, this would give you full marks. If you wanted to, you can move this into the denominator because it has a negative power, which and then we also have the 2 here, which we could move, and that would make it a little bit easier. But I mean, honestly, I would just leave it just like that. It would actually make it very nice because the square roots will go away, but it's okay. Number 5 is very funny. Natural log of e to the x. If we have h of x is the natural log of e to the x, can anyone tell me why that's a funny question? Let's solve it and see if anyone figures out why that's funny. Okay, again, what is our rule? Natural log means we copy the bottom. Yeah, we copy what's in the brackets to the bottom and differentiate it to the top. Yeah, e to the x, the derivative of e to the x here is what? Is e to the x, which is 1. Are you surprised that the derivative here is 1? Oh, is it 1? Did I do something wrong here? Oh yeah, no, that's correct. Yeah. Yeah, it's correct. 1 is correct. Now, why did I say this was a funny question? Because technically, if you look at natural log and e are opposites of each other. So if you were to simplify this, this would literally just be x. So if anyone spots this, that this is x, the derivative here is a very nice present, very easy. Okay. Is there any specific question you want to see, or did you want to move on and do something else? I think those are all pretty good examples to do. Yeah, let's have a look at the next part. So if we have a look at trig functions, yeah, there's a formula sheet that we get. So sine of x differentiates to cosine of x. Cosine of x differentiates to negative sine x. We just need to remember which one goes to which. And we have to be very good at remembering which one is which, because if we integrate, we need to make sure we're not missing the negatives or the positives. There's some more. Let's see if I can remember them. Tan is, I think, secant x if you differentiate it. And there's a bunch more, and I don't remember any of those. But they're in a formula sheet. If we ever need them, I'll pull them up. Okay, so let's have a look at the first and 2 are very easy. Let's have a look at number 5. Let's do number 5 here. We have f of x is equal to cosine 3x. Now, how do we do this? We see there is a cosine here. Yeah, so we want to differentiate that. So let's do f prime of x. We know cosine goes to negative sine. So we're going to replace it with negative sine. And whatever is in the brackets, we're just going to copy. We're just differentiating the cosine part. So we're going to copy the 3x. And what's the next part here? Can you spot what's missing here? Let's have a look. There's one part that we still need to do. Let me set up the next question already while you guys get a chance to have a look what's missing. Sine squared x. Let's do this one. Minus 3 sine 3x. Yes, correct, because we need to multiply by the derivative of the inside function. Very good. Awesome. And if we have g of x here, let's do g prime of x. Now, again, we have a little 2 here. So what does that mean? That means we have a power. This whole thing is raised to a power. Some people prefer rewriting this with a squared over here, Mathematicians are very lazy, so they put the 2 on the sign. Now this is chain rule because we have something in brackets. So we're going to copy exactly what we have here. And actually, I want to change this to having a 4x in the middle as well. I want to make it a little bit harder. Yep. So let's have a look. So we have 2 in front. Then we have a sign. We copy what's in the brackets. And then we have to multiply by the derivative of the inside again, right? Oh, hold on 1 second. So this is this part here, right? To the 1. And then we have to multiply by the derivative of the inside, which is cosine 4x, which is exactly what you had in the chat for the one before I changed it. Very good. And now we multiplied by the derivative, but the derivative here itself has an inside function. So we again need to multiply by the derivative of this inside function here. Yeah, so some of those questions can get very fun if you've got multiple chain rules and quotient rules. And again, for people who are watching this later on YouTube, if there's any specific questions you guys want me to do, I'm always happy to add them in the chat or in the comment section later. Now there's a couple of mixed questions. Maybe you want to have a look if you want us to do any of those. Otherwise, I will move on to finding the equation of a tangent and a normal for a function. Okay. Okay, let's have a look at a tangent and a normal. Now we've briefly, there's some more examples. We can leave that for later. That's okay. For the tangent equation and the normal equation, let's briefly remind ourselves what those mean. If we have our x and our f of x over here and our function f, then the tangent line, that was what we discussed before, at this specific point is the straight line that has the same gradient as our equation. What is the normal? Yeah, so maybe I put in here, this is the tangent. Yeah, so we have the same gradient. And the normal is also going through that exact point. However, it's on a right angle to the tangent. This is our normal. So how do we find the normal, or what do we know about the normal? The normal is perpendicular. Yeah, so that means on a 90-degree angle, yeah, to the tangent line. Does the concept of the same coordinate geometry also? Yes, there's also a concept in geometry. Tangent for tangent, that's exactly the same thing. Yeah. So when we talk about a tangent, we mean a line that just barely touches a curve or some other line at that one exact point. Yeah. For example, I'll just quickly draw this here. In circle theorem, there is, in geometry, there might be a circle here, and if we have a tangent, two tangents that meet, oh my god, I'm terrible at drawing, then we know that this distance from here to the point and here is the same. Yeah. So again, these are tangents because they have some kind of curve, which is the circle here, and they touch it at exactly one point, and the gradient at that point is the same. So what we need to do here is we want to find the equations of a tangent and a normal. And we know both of those are straight lines. So they're both going to be in the form of y is equal to mx plus c, where m is the gradient and c is the y-intercept. So let's have a look how we can do that. I'll make up a question over here. So let's say we have find the equation of a tangent to f of x is equal to 3 sine cosine x when x is equal to 0. Okay, so what do we what do we need? We have some kind of function. We have no idea what it looks like, but we want to find the equation of a tangent. What do we know? We know, and that's our first step here, that the gradient of our function is the same as the gradient of the tangent. So we can use our original function, or our function here, to find the gradient of that tangent. And everything that has to do with a gradient means differentiation. So we have f prime of x is equal to, now how do we differentiate this here? We see a sign here, and we see something inside sign. So what we're going to do is we're going to copy, yeah? So first differentiating sign, sine goes to cosine, 3 cosine, and then we copy what's inside, and then we multiply by the derivative of the outside function. So this is the copied part. We need to now multiply by the derivative of cosine, which is negative sine x. Again, we're not going to simplify. This is not an algebra class. We're just going to leave it as it is. And that's our equation already. Oh yeah, that's right. We wanted to do a couple of other things, but we can do later. Okay, so when we look at these now, how do we now find the gradient? Well, we need to substitute in a value for x to find the derivative, which is the gradient. So we're going to have the derivative evaluated at x is 0. And if we change all of the x's here to 0, so if we substitute, then we get all of our values. So we're going to get 3 cosine of 0 times by negative sine of 0. Sine of 0 is 0. So multiplying by whatever this is will be 0. But just so you can have a check, cosine of 0 is 1. Cosine of 1 is a little bit harder to find, but it doesn't matter because this part here is 0. Multiplying by it will equal to 0 as well. So what does that now mean? If we have f prime found, evaluated at 0, that means that is our gradient. Yeah, f prime evaluated at x0 is the gradient at the point x0. Okay, so once we have the gradient, remember the gradient of the function is the same as the gradient of the tangent. So that was this part here. Yeah, the gradient of this function over here is the same as the gradient of this tangent line. So we can take that into our calculations. Yeah, so we now have found that the gradient is 0. Now, what else do we need to do? Well, let's have a look. Our tangent line is mx plus c. We have found our gradient. So we're going to get m is 0x. Well, that just means 0. But we still need to find c. We need to find the y-intercept for this question. So how do we do that? Well, we know that the tangent line goes through the same point as the function itself. So we need to find the coordinates x0, y0 of the point of intersection. So how do we find that? Well, we know the x value. We know the x value is 0. That was literally given to us over here. And how do we find the y value or the function value? Well, this function here gives us the y value. We just have to use this one here and substitute in 0. We had sine of cosine. Okay, so we have now f of 0 is equal to sine of, was it 3, right? 3 sine, sorry about that. Yeah, 3 sine cosine of x. But now we're going to replace the x with a 0. And we're going to evaluate what that number is. This is 3 sine cosine of 0 is 1. And unfortunately, I don't know what the value is for 3 sine 1. So let's just quickly have a look. If we go over here, 3 times, can I do sine like this? No, I don't think I can. Sine of 1. So we have about 2.5. Let's just round it to 1 decimal place. That's more than enough, 2.5. So if we have 2.5 as our y value, now what do we have? Now we have our coordinates, 2.5 for y and 0 for x. And once we have this, now we can go back and we can put it into our equation and find out the full equation. So we're going to use our x that goes in there. We're going to get our y, which goes in there. And this is a very easy one because m is 0, so there's no x. So we're just going to get y is equal to 2.5. So what do we know here? We know that now the equation of the tangent line is exactly that, or more specifically 0x plus 2.5. If you want to check out, make sure it's a straight line. Okay, now what about the equation of a normal? The normal is the one that's perpendicular, so that's on a 90-degree angle to the tangent line. Now, I'll need to give you a different example here because it's a little bit boring otherwise. Let's say we want to find the equation of the normal. For our equation, h of x is equal to e to the that's a silly example again. E to the square root of x. Let's just do that. Plus sine x. And again, it doesn't really matter what x is, but let's just say x is 0 because hopefully that's going to give us some easy calculations without a calculator. But it doesn't matter if I make it 10, you guys can just use a calculator to figure out that answer. Now, think again, what are the things that we need for the equation of a normal? The equation of a normal is a straight line. So we have mx plus c. So we need the gradient, and we need the y-intercept. So which one do we start with? We can easily start with a gradient because we know differentiation. So every time we have a gradient, we need to find the derivative and then substitute in. So what is our derivative here? H prime of x. Well, first we take the derivative of this part. And what did we learn? Anything with e, every function with e, is just copy it, right? E to the square root x. And then don't forget to multiply by the derivative of whatever the power is. Yeah, the inside function. That's chain rule. So, and we've done this a couple times now. X to the power of half differentiated is 1 over 2 x to the negative half. Yeah, it's always good to kind of keep that in mind. Put that in the corner if you need it. So this is going to be 1 over 2 x to the negative half. And now we need to differentiate this part 1 by 1. So we're going to differentiate sine of x, which just becomes cosine of x. And what do we need to do here? So for next part, if we want to find the equation of the normal, we need to substitute in 0 here to find the gradient. Hey buddy, NCEA is the New Zealand curriculum. This is the mathematics exam for New Zealand. Okay, so if we want to find the gradient, that is the derivative substituted in a value, which is our x value, which is going to be e to the square root of 0 times 1 over 2 times 0 to the negative half plus cosine of 0. And again, we have this whole part here is 0 multiplied by this is 0. This whole thing is equal to 0. And cosine of 0 is 1. So the answer here is 1. Can I squeeze that in without having my face in? There we go. So if the gradient is 1, now we have our gradient, but we still need to have the y-intercept. So if we want to find the y-intercept, what did we do before? We need to substitute in a point. Let's have a look. So in order to find that, we again needed to have our coordinates x, y, right? We already have x, so we just need to find y. And where do we find y? That's in our original equation. So if we substitute in 0 into our original equation, that is where we get our y value from. So let's do that. E to the square root of 0 plus sine of 0. Now let's have a look. The square root of 0 is 0. E to the 0, any number to the power of 0 is equal to 1. So this is 1. And sine of 0 is 0. So again, we chose a good example. We can do this without a calculator. The y value is also 1. Yeah, I mean, this is very standard differentiation stuff. So it doesn't really matter which country you're in or what exam you're studying for. Differentiation for university, differentiation in high school, engineering. This is a very fundamental course for differentiation today. Of course, we're focusing on the New Zealand curriculum at the moment, but everything that we're discussing here, you will basically see in all other countries applied the same way. By the way, the students in New Zealand who take this are 17 or 18 years old. This is in their last year of high school. Okay, now where we have a y value and we have our gradient and we have our x value, now we can go back to our equation and solve for the y-intercept. Let's do this over here. So we get y is equal to mx plus c, and we substitute in all of those numbers that we've got. Y is 1, m we found as 1, x is 0 plus c, and I mean, this is a very easy example. Again, I'm glad that the numbers are working out, then I don't have to use the calculator so much. C is 1. So this here would be the equation of what? We did not find the equation of a normal. What did we find the equation of? I'm sorry, I have no idea how to do machine learning in New Zealand. Okay, if you guys paid good attention in our last example, that's exactly what we did to find the equation of a tangent. But we wanted to find the equation of a normal. So there is one last step that we needed to do. Yeah, I wanted to see if you guys in the chat are paying attention. There's one last change, and that is the gradient change. Because remember, when we look at our picture over here, we said that the normal is on a right angle to the tangent line. So clearly they can't have the same gradient. Now, how do we find a gradient that is a 90-degree angle, a right angle? Well, there's a very easy way to do that. The gradient for the tangent is 1, but the gradient of a normal is -1 divided by the gradient of the tangent. So you guys can write this one down if you guys ever need it. This would not be on a formula sheet. Yeah, it would be expected that you guys know that you have a -1 and you just divide by the gradient of the tangent. So let's put our numbers in. So we have -1 divided by 1 is -1. So our gradient is actually -1. So with that in mind, now we can do exactly the same thing, which is substituting in our values into our equation of a straight line. Our y value was 1. Our m value was -1. The x value was 0. And c is what we need to find. Again, this is nice. It's 0. We're going to get 1 is equal to c. I'll kind of scooch over a little bit. And we can write our final answer, which is y is equal to -1x plus 1 as the equation of the normal. There we go. All right. Very, very productive already today. We've got about half an hour to go. We've covered the fundamentals in differentiation on how to do all of the different equations. We've got trigonometry, we've got a trig functions, we've got e to the x, we've got natural log, we have product rule, quotient rule, chain rule. We've found the equations of a tangent, the equation of a normal, and all of these step-by-step instructions you guys can just copy and paste. Just if you guys have to, go back in the video, rewatch it another time, and write down all those steps one by one. Every time they ask you to find the equation of a normal, of a tangent, or anything like that, it's always the same. Maybe for the next half an hour, we can talk a little bit about optimization, which is finding critical points in using differentiation. So let's have a look. So first of all, we kind of need to know what are critical points. Let's have a look at this graph here of our very common f again. Now, if we want to know what the gradient is, right, then we can use the derivative and substitute in a value. So that will find the gradient. But when we what we really usually want to know is specific points on this curve. And these are the critical points. And they are also called turning points. Yeah, so they're also called TP, turning points. They are there's a few that different names here. Let's just stick for critical points at the moment because I want to classify them in just a second. So what are critical points? There's three types of critical points that we need to worry about at this level. One is your minimum. The next one is a maximum. And the last one is a point of inflection. So let's have a look on how all of these look. I'll draw a very quick picture for each. Well, if we have a equation here, and I'll actually just draw the function itself, yeah, then this point here is a local minimum. Yeah, the reason why I say local is because potentially somewhere else is another minimum that is lower. Yeah, this would be a global minimum, which is the lowest point on the whole graph. Some graphs may not have a global minimum. Let's say this goes infinitely further down. There's no global minimum here. If we have this, then we have a local minimum. Sometimes a local can also be a maximum. A local minimum can also be a global minimum, which in this case is the case, as long as we assume it's cut off there. It doesn't go down. Okay, the next part is your maximum. So let's have the same kind of graph, and a maximum again is the highest point over here, and we also have a maximum somewhere over here if this continues to go down. These are all local maximums, and then again this one here is the global maximum. What is the point of inflection? A point of inflection kind of looks a little bit like an S. It's not very clear. There we go. That's better. Here, this point here is a point of inflection. And later on, we will see that a point of inflection is defined to where it changes concavity. So over here, this graph is concave down, and here this graph is concave up. But at the moment, we don't need to worry about that. That is something that we're going to cover in our second part for the differentiation part. We go live every Monday, 6:30 to 8:30 to discuss the differentiation topics. So these are now our three types of critical points. If we're considering these three types of critical points, there's a few here on the graph. One is here, that's a maximum. We have a minimum here, and these points here seem to be where we change concavity. So now when we look at, oh, I didn't want to delete everything. Yeah, I just want to focus on the maximum and minimums for now. Now, when it comes to finding those critical points, let's have a look what those maximums and minimums have in common. So if we are at the maximum, if we draw a tangent line as well, then this is what it's going to look like. And this was for the maximum. And if we do this for the minimum, then we're here and we have this. Now, this is for every maximum and every minimum. They're all the same. And what we can see here is that the gradient of both of those is actually 0. So when we are looking at our critical points, especially the maximum and the minimums, we always need to remember, as soon as we see maximum, minimum, point of inflection, critical point, turning point, any of those terms, we immediately need to write down that the gradient is 0, because that's always the case. And knowing that is always going to help us find the solution here, knowing that the gradient is 0. Well, we're in the differentiation topic, so how do we find the gradient? It's always taking the derivative, and then that is the gradient if we evaluate it at a point. Too much talking. Let's see an example. Let's do a couple of examples so we can actually see what's happening. Let's first of all, let's try our very common x squared. Yeah, just to kind of remember how to do this and what it means. And we all know this is the quadratic that looks like this, x squared over here. And what do we expect? Well, we expect to have a minimum at the point 0, 0. So from our knowledge from graphs, we already know what the answer is, but we're going to learn step by step on how to find critical points with any equation, no matter how difficult. So the first step is always gradient is equal 0. Why is that the case? Because we have a minimum or maximum. So every time we talk about a gradient, we know that is the derivative. So we're going to go to f prime of x is 2x, and we know that that is 0 because that is the derivative. And now we get a new equation, which is this part over here, that we can solve. So how do we solve this? 2x is equal to 0, divide both sides by 0, x better be 0. And now what we found is the x values for critical points. Yeah, this is the x values for critical points. So what do we do with that? Well, we don't actually know if it's a minimum or maximum at that point, if we didn't have our picture here. So what do we need to do? Well, first of all, we need to have the full coordinates. Yeah, so we also need the y coordinate, which we get from our original function. We know that x is 0, so we can now plug that back into our original equation to find the y value, which is also 0 here. So just like we expected, at the point 0, 0, there's a critical point. But how do we classify if it's a minimum or maximum? Well, we will talk about a strategy or a method on how to do that in just a second. There's 2 different ways that we can do that. For now, we're just going to focus on making sure that we get all of these correct, finding all of the points. So let's do another example. Let's do f of x is equal to okay, e to the x. Let's do e to the x. So if we now want to find the critical points, how do we do that? Step by step. Well, critical points means gradient is 0. And every time we have the gradient, that means we have the derivative equals 0. So let's find the derivative of x here. And we know the derivative of e to the x is e to the x. And we know that it's 0 because it's the gradient is always 0 at critical points. So now we need to solve e to the x is equal to 0. Well, e is a positive number, 2.7, and it doesn't matter what power we use. It doesn't matter. It's never going to be 0. And if we look at the graph for e to the x, which looks something like that, e to the x, we can see it's never in the negatives. And it's also never touching 0. It's got an asymptote at 0. So there are no critical points here. But I mean, if we look at this graph, this makes sense because we know it's constantly increasing. So there can't be a minimum or a maximum. Okay, one more example for finding critical points, maybe one where we have a few points. Let's say we have f of x is equal to x squared plus 1 times, let's do, we can just do another polynomial like this, 3x. So how do we differentiate this? First, well, the derivative here can be used by product rule or by expanding the rules first, but that is one of the equations that we did earlier on. We can just expand this here, expand the brackets, 3x times this and 3x times this to make it easier for us later. So we're going to get 3x squared plus 3x. And we don't know what that looks like, but if we want to find critical points, we know immediately one thing, which means this means m is 0. The gradient is 0. So every time when you're asked to find critical points, maximums, minimums, turning point, point of inflection, all the same. We're going to write m is 0. And we know that the gradient is given by the gradient function, which is the derivative. So we know that that is 0. And we can also find the derivative from this by using the power rule, which is multiplying the 2 to the front, which gives us 6x plus, this one is 1 at the power, if you need to use the power rule, 3. And now this, oh, did I make a mistake? My bad. I talked too much. Of course, this is to the power of 3 here. Yeah, I was going to say that didn't make much sense there. Apologies. Now, let's differentiate again. So we get 9x squared plus 3. Do it right this time. Very good. And now we know that this is equal to 0. So let's solve this quadratic here. We don't need the f prime anymore. We have now 9x squared plus 3 is equal to 0. It's a positive quadratic that's moved up. So it looks something like this. And again, there is no solutions for this question. Yeah. So we have no possible x values in the real numbers for this. So that means we don't have any critical points here again. Yeah. Okay. Next question. Okay. So what have we done? We've done all of our fundamentals. I think we should do one more thing before we finish, and that is part of the critical points one. We need to classify what the critical points are. So that means there could be a minimum, there could be a maximum, or there could be a point of inflection. And in order to do that, there's two kind of tests that we can use. Let's have a look at our equation, which is again x squared. Very badly drawn, but that's okay. There we go. So here we have x squared. So we know that this question here has a minimum. And if we want to find this minimum from graphs knowledge, we know it's at 0, 0. And we know it's a minimum. We did this question earlier on, and we found this 0.00 using differentiation. But we didn't actually know from the calculation if it was a minimum or maximum. For all we know, without knowing the graph, it could have been a maximum as well. So let's have a look on how to classify our critical points. So let me just move over, expand the canvas a bit. There we go. So when we want to check if we have a minimum or a maximum, we want to have a look how the function looks around that point. So here we are increasing before that point, and afterwards we are decreasing. And the other point, the minimum, is first decreasing and then increasing, which is of course very easy when you look at the picture. So there's two things we can do. The first method is by checking locally. Yeah, so we're going to check locally if we're increasing or decreasing. Well, how do we do that? Well, the derivative evaluated at some point a little bit before our critical point. Yeah, so if we have 0, 0 as the critical point, like before, we might want to substitute in -1. If we find the derivative of a little bit before the point, and we know it's increasing, so it means it's greater than 0, then we know that afterwards, yeah, if it's afterwards decreasing, then we have a maximum. So this is your maximum. We first increase, then we decrease. So if we have f prime evaluated at a different point, a little bit to the right. So let's say we have this point here was x0, this point was x1. And if we have a look here, just before it, we're increasing, just after it, we're decreasing, then we know, then we have a maximum. In this case, decreasing means our gradient needs to be negative, so less than 0. Now, if we already have the derivative, this is a very easy way to just substitute some numbers in. So let's just try and see what we get. Yeah. We had the example where we have f of x is equal to x squared. And if we differentiate it, we get f prime of x is 2x. And now what we found is that the x value is 0 and the y value is 0 for our critical point. But now if we want to check if it's a minimum or maximum, what we're going to do is we're going to evaluate the gradient just before, and we're going to evaluate the gradient just after the critical point. So we're going to substitute in -1, which is -2, and 1, which is 2 times 1 is 2. And we don't really care what those numbers are, but what we note is this one is positive. Oh my God, this one is negative, and this number here is positive. So for a value just before our critical point, yeah, remember this one is the before, this one is the after. Just before the critical point, we are decreasing. So we're first decreasing, then we have a critical point, then we're increasing. That must be a minimum. Yeah, and this is a check that you can do whenever you just want to substitute some numbers in. That's fine. You have a calculator, so just pick something just before. And even if you do, like for example, 0.9 and 0.1 and -0.1. Yeah, so we want to get close to it. Oh, sorry about that. It's kind of behind me. Yeah. Okay. Now the last part. And this is the method that most people use to classify critical points. The last one is to use the second derivative test. So we have the second derivative test. How does this work? Well, if it's the second derivative test, we probably need f double prime. And let's have a look how this works, and then we apply it. So double prime just means that we have the derivative of the derivative. So we're going to take the derivative twice of the original function. And this is the test, right? So first, if the double prime evaluated at the critical point, we substitute in the x value, is less than 0, then that means we have a maximum. So it's kind of opposites. Less than 0 you would think is small, but that makes a maximum. And if f double prime evaluated at our critical is positive, then that would mean that we have a minimum. Lastly, if f double prime evaluated at this point is equal to 0, officially the correct way of doing this is stop. This is not defined. We don't know what it is. It could be anything. So we don't actually have a conclusion. No idea. Now, if you guys are sitting the NCEA exam, you guys can assume that double prime, f double prime equals 0 means point of inflection. So let's make this very clear here in dark green. F double prime evaluated at x is equal to 0 means point of inflection only for NCEA Level 3 exams. So if they ever ask you to find a point of inflection, they mean the second derivative is equal to 0. They're not going to give you any questions where this doesn't work. And they assume that you don't know this. They assume that you immediately know that point of inflection means this. Okay, let's use the second derivative test for a couple of examples. But one thing that I still wanted to say, and that is that these parts here actually show you how the graph looks. So if the second derivative is negative, which is our first case here, our graph looks something like this, which is called concave down. And the other way around is concave up, when the second derivative is positive. And now the way that I always remember these is one, we have concave up is like a cup. So we have like a teacup. You can kind of hold it there and drink your tea. And concave down is like a frown. So if you make two dots on there, people are unhappy. People are very upset. So they're frowning. So concave down is like a frown. Concave up is like a cup. So when we do this test and plug in numbers, we can see the kind of general shape of what our function looks like. Okay, let's see it in action. Let's go scroll down and do a couple of questions. Okay, so find and classify all minimum or all critical points. Let's just do that. Okay, f of x is equal to, I kind of want to have one that has a few, so let's do negative x cubed minus 4. Let's do minus 4x squared plus 6x plus 1. Hopefully we get a few critical points here. We know it's a cubic that's negative, so we're expecting two solutions here, one minimum, one maximum. Hopefully it's not a cubic that looks like this with a point of inflection, but it shouldn't. Okay, so let's have a look. First of all, in order to find our critical points, what is our rule? Our rule is the gradient is 0, so that means the derivative is 0. So f prime of x is equal to negative 3x squared minus 8x plus 6. We've done this a lot in the beginning. Everyone should now be able to follow with the power rule here. And we know that this is equal to 0. So now we can solve this equation over here. Now, how do we do that? Well, we can see if we can factorize, but probably not, because I've just made that equation up. So let's go to our calculator. and we're going to go to menu and go to the equation section. And here we have a polynomial, which is f2. There we go, of degree 2. We have a quadratic, so the highest power is 2. And we have -3 is the number in front of the x squared, -8 is the number in front of the x, and 6 is the number by itself, equals 0. And we can see here that we got 2 points. We got x1 is 0.6. Let's just round it to 1 decimal and call it a day. And the second one is x2 is equal to -3.2. So these are now our two x values for our critical points. So at those parts, we can either have a maximum or we can have a minimum. Well, how do we do this? Well, first of all, we need to know the coordinates. So we have 0.6, comma, and then the y value, and then -3.2 and the y value. How do we find those values again? Well, we need to substitute these values x1 and x2 into our original function. And I'm just going to cheat and write here f of 0.6 and here f of -3.2. And I'll leave it up to you guys if you guys wanted to put these numbers into the calculator to find the exact value. For now, we're just going to call this our critical point 1 when x is 0.6 and critical value 2 when x is -3.2. For completeness, we need the coordinates, but let's skip that part. Because now we wanted to do the second derivative test. We wanted to see if we have a minimum or a maximum. So let's take our second derivative here, f double prime of x, which is the derivative of this one here. And again, we've done enough questions today to be able to do the power rules to get to -6x minus 8. Now this is the double, the f double prime. So what was our rule? We said that if the f double prime is negative, that means we are concave down, we have a maximum. If the second derivative is positive, we have a minimum. And if it's equal to 0, we don't know. So we're just going to have to substitute in our values for our critical points. So we're going to get f double prime evaluated at 0.6 and f double prime evaluated at -3.2. So that means just substituting it in 6 times 0.6 minus 8 and -6 times -3.2 minus 8. And again, we don't care what the actual answer is, but we can see that this is a negative number minus another number. That is definitely going to be a negative number. It's less than 0. And here, negative and negative makes positive. 6 times 3 is more than 18 here, so -8. So clearly this is a positive number. And just like expected, one of them is going to be a minimum and one of them is a maximum. Okay, ask yourself real quick, which one is which? Yeah, so negative value for double prime means it's a maximum and a positive means it's a minimum. And this is an easy way for you guys to justify in your, especially your excellence questions and merit questions, why a certain value is a minimum or a maximum. Okay, we did a lot of questions today. We covered a lot of topics. Remember guys, every Monday 6:30 till 8:30. Yes, my cat is coming now apparently for a cuddle. She knows it's time for us to end the stream. Yeah, yes, I'll feed you now. Okay, I'll see you guys in the next stream. Next week we'll finish a few minutes early, but that's all right.